capai misi yang satu, permisi kita bantu.
Tahniah, siaran langsung ini dibawakan khas kepada anda oleh Akademi Youtuber Malaysia. Tumpukan perhatian anda, siaran langsung akan bermula sebentar lagi. Link sijil akan diberikan di hujung siaran ini. Pastikan diisi dalam tempoh yang ditetapkan. Terima kasih.
Hi, Salam, Sejahtera, and good evening, everyone. Welcome to Pusat Tuisyen Akademi Youtuber with joint venture of e-Delay Malaysia and Club Guru Malaysia. I am Mr. Peh. Currently, I am teaching at College Tingkatan 6 Tun Fatimah Melaka. I am the on-duty teacher for this week. For information, as usual, this week we have 2 free class Fizik SPM are preparing for you. So the Form 5 class will be as usual here on Friday, 9:30 p.m. And for this week, it will be presented by the teacher Slinda. And for Form 4 class will be presented by me. And the class for Form 4 DLP will be held on every Sunday, 8:15 p.m. Okay, so the lesson for today will be take about 1 hour to complete. So in the line here, we have Yamuna Sri. Thank you to join my class. Yamuna, please tell me where are you come from. And we have Jaing also. Hi Jaing. Apa khabar? Khabar baik Jaing. And we have Kavia also. Thank you, Kavia. And also Jimmy. Hello, Jimmy. So everyone, thank you for joining my lesson. Okay, so today I am going to complete the chapter 3 with the last topic 3.3. So the topic will be man-made satellite. So and in this topic, you are going to learn about 4 learning standards. Okay, so and the link schedule for today's lesson will be sent at the end of the class letter. And please fill out with any email you are available. And please fill out within 30 minutes. Okay, so without further ado, let us start our lesson today. Okay, so this will be the first learning standard for today. So you have to able to describe how an orbit of a satellite is maintained at a specific height by setting the necessary satellite velocity. Okay, so that means that you need to understand how to maintain the altitude of the specific satellite by relate it with the satellite velocity. Okay, actually the satellite velocity here is the linear speed of satellite where you learn already at the learning standard at the start topic at 3.1 and 3.2. Okay, so let us go through learning standard 1 together here. Okay, hi Yamuna. So where are you come from? You may write your school and which state are you come from in the chat room. Okay, so here, the first, let us define the satellite. Okay, so a satellite is any celestial body that orbits around a large planet. Okay, so here we have example. So in this GIF, you may see that the moon is revolving. Okay, so it's revolving the Earth. So the moon is a satellite of the Earth. And you can see also, parallelly, the Earth is actually orbiting the sun. So the sun is actually the satellite of the sun. Okay, so this is a natural satellite where we can observe here. Okay, so how about the man-made satellite? So a man-made satellite is an artificial object launched into space to orbit the Earth for specific purposes. Okay, so the satellite, man-made satellite here will be orbiting the Earth, just like the moon orbiting the Earth and the Earth orbiting the sun. Okay, so the concept is actually the same. Just man-made satellite is an artificial object. Okay, hi. So here we have another. students, Mei. Okay, thank you, Mei, for joining my lesson. Okay, so the first man-made satellite to orbit the Earth was a Russian satellite. So we know as Sputnik 1, which is already launched on October 4, 1957. So this is the appearance of the Sputnik 1. Okay. Okay, then the number 3. Okay, so as of 2025, there are approximately about 11,200, actually 700 active man-made satellite orbiting the Earth. Then with 1,000 more inactive satellite being tracked by space agency worldwide. So you can see for the active satellite, we have about 11,700. So the number is actually many. Oh? Okay, hi, good evening. Chayao. Okay, fine, here. Okay, so thank you everyone for joining my lesson. Okay, so here, number 4. Okay, so here we have a satellite in Malaysia. So currently, Malaysia has several satellites, including privately owned communication satellite. Okay, so here, Malaysia, we have communication satellite where already launched since 1996. So the first satellite of Malaysia is actually launched 1996. So the satellite name is Mersat 1 and Mersat 2. So here we have others Mersat series where will be where was already launched at 2006. The Mersat 3, 3A 2009, 3B 2014, and another Mersat satellite 3D at 2022. So all of this Mersat series is actually the communication satellite. Okay, so besides the communication satellite, so Malaysia is also launch others type of satellite here. So you can see, in addition, Malaysia has also launched other type of satellite such as Tionsat 1, Razat 1, Razat, UITM, Sat 1, Sat 2, and the latest one just launched this year, Usmat Sat 1. So the purposes including Earth observation, scientific research, and technology development. Okay, so here is about, I think it's about 10 satellite was launched by Malaysia here. Okay, so here, the working principle of the man-made satellite is actually the learning center 1 where you need to understand. Okay, so here, gravitational force provides the necessary centripetal force to keep a satellite moving in a fixed orbit around the Earth. Okay, so you can see from the figure, we have black spheres surrounding or orbiting the Earth. Okay, so it has labeled with V. So the V is a linear speed or the satellite speed here. And then the A is actually the acceleration. Okay, so the centripetal acceleration A, you learned already with the formula of mv squared over r, right? So if this is a F, so the A will be v squared over r. Okay, so the centripetal force where have the same direction towards the Earth's center, labeled as A, is actually causes the object to orbiting the Earth. Okay, so here the satellite move in circular orbit at specific altitude. Okay, so the altitude will be here from the center of Earth to the orbits labeled here. So the height here is actually we know as the altitude. Okay, and then you can see the black spheres is actually represented as the satellite is moving with V. The V is the linear speed, or we also can know as orbital speed. Okay, sometimes they're using orbital velocity because the magnitude is almost the same. However, the direction is always changes now here. Okay, then V, linear speed is the speed of an object that remain in orbit at a certain altitude. So that means the linear speed is a speed for the satellite to maintain at the same altitude. So that means at the same height, same distance from the center of Earth. Okay, so here, the concept of centripetal force. Okay, so where you learned already, at 3.1, sub-topic 3.1, and Newton's law of universal gravitation. Both of these concepts is actually used to calculate or form the linear speed formula. Okay, you can see from this figure. So the red arrow showing the attraction between two objects here is between the moon and the Earth. Okay, so this is the application of the Newton law of universal gravitation. So we're using this formula. Okay, F1 equal to Gmn over R square. Okay, and then at the same time, for the moon to orbiting the Earth, it is actually added by the force we know as a centripetal force. Okay, so the centripetal force formula will be mv squared over r. Okay, so from the two concepts just how we mentioned, we may able to derive the linear speed formula for the satellite. Okay, so here, as mentioned just now, so we can imagine that we have a satellite orbiting the Earth. So the mass of the satellite is represented with the small m. Then the capital M will be represented as the mass of the Earth. And then we have R. So the R will be the distance between the satellite to the center of the Earth, or we know as the altitude or A1. Okay, then the linear speed is actually here. It's a satellite speed. If let's say you're referring to the sentence used in the learning standard one just now I mentioned to you. Okay, so here, as mentioned just now, we are going to use the concept of first law of gravitation of Newton. So where the formula will be Gmm over R square, or we have the formula where will be F equal to Gm1 m2 over R square here. So the m1 here referring to the mass of the Earth, and then the small m here will be the satellite actually, or in this figure represented as the moon now. Okay, then the R square will be the distance between two objects, center to center. Okay, so here the second concept we are going to apply here will be the centripetal force. So as mentioned just now, the centripetal force is a force to maintain the object to orbiting the Earth. Okay, will be this. The formula will be mv squared over r1. Okay, any question you may ask me in the chat room. Okay, then from here the F1 is actually equal to F2. So we have Gmm over R squared equal to mv squared over r. Okay, then we have to cancel out small m. What else we can cancel? It will be r, Okay, so we left Gm over r equal to v squared. Then we rearrange, we get v squared equal to Gm over r. Will be this v squared equal to Gm over r. So we get the formula of the linear speed, v equal to square root Gm over r. Okay, so from here you can see that actually the linear speed is depends on G, M, and also R. But G is a constant with fixed value, where will be 6.67 times 10 power negative 11. And then the capital M is the mass of the Earth, is also fixed. So there will be only R, which is orbit radius affecting the linear speed. Okay, so here will be this, the discussion. So since both G and M are constant, these two is constant, the only factor that affect the linear speed of the satellite in the circular orbits will be the radius of the orbits. So that means only R will be affecting the value of the V here. Okay, so as the radiance increases, okay, you can see here, we take out G and M. The V will be actually inversely proportional to R, right? So here, when the radiance increases R, so the value of V or linear speed will be decreases, or vice versa here. Okay, so this what you are actually need to understand for the learning center 1 or A1. Okay, then 7, if the linear speed is too high, the satellite will overcome the Earth's gravitational pull and may escape into space or move into higher or unintended orbit. Okay, so you can look at this figure. So the orbit velocity actually is the linear speed of the satellite. Or bring the same meanings I want. Okay, so you can see the blue line. If the satellite moving at the linear speed or the orbital velocity, so you can see the distance or the altitude is always the same for the satellite. However, here we have another 2 cases. So you can see here we have the red line show with the slow motion. Another will be the greater speed than linear speed or orbital velocity. Okay, so here the sentence number 7 actually tell you if the linear speed too high, represented with the green arrow here. So you can see the satellite will be able to overcome the attraction of the Earth gravitational pull and able to move to higher position. Okay, so they will be moved to new orbits already. So the orbits is the orbit where mentioned as unintended. That means that it's not we want actually. Okay, then another case will be if the linear speed is too low, represented with the red line here. Okay, so the gravitational pull will dominant. So that means the satellite will be moved towards to the Earth already and causes satellite to spiral downward. So we're moving down and eventually re-enter Earth atmosphere. So you can look at this figure. Okay, so when we enter the Earth atmospheres, the satellite will be burned because of the friction between the satellite with the atmospheres. Okay, so this is the impact if the satellite is not moving at linear speed. If too fast, it will be moving higher or moving higher. If too slow, it will be moving lower or go towards the Earth. Okay, so this is the impact for the V to the altitude or the orbital radius of the satellite. All in one. Okay, I hope you all can understand. Okay, so you can respond to me if I say you understand what I discussed here. Okay, so we have actually finished already our Learning Center 1. So let us go through one example question related to Learning Center 1 here. Okay, so let us read the question together. Okay, so here, diagram 5 show the man-made satellite and the moon orbiting the Earth. Oh, moon is here, then the satellite is here. So a force acts on the satellite and moon that allowed them to move in circular state. So the force here is actually referring to centripetal force, A1. So the period of orbiting the Earth by satellite and moon takes about 1.5 hours and 27.3 days respectively. Okay, so here will be the 2 satellite. One is moon, another one is man-made satellite. Okay, so they have their orbits. Okay, so here, name the force that caused the man-made satellite and the moon to move in circular orbits. Or if you got idea, you can type answer in the chat room. Okay, so here, ask you about the force. Actually, just now I mentioned to you already. So this will be the force causes the moon and the man-made satellite to orbiting the Earth. Okay, so the force is actually centripetal force. Okay, or you can give also gravitational force. Okay, then B. Okay, so B will be conception question here. A1, you can see here. The question asks you to compare first the orbital radiance. Okay, so the orbital radiance of the man-made satellite with the moon. Then second, ask about the period of the man-made satellite with moon, and then linear speed of the man-made satellite with the moon. Okay, so here we actually can just observe the diagram to get the answer. Oh, okay, so here the orbital radiance we're referring to R, where here will be the 385,000 km. Okay, then for the man-made satellite, actually given you H only, exclude the R, right? Okay, exclude the R. However, if you look at the orbits of the moon is further from the Earth, right? Okay, so I think it's very clear to show you from picture that the orbital radiance for the man-made satellite is actually smaller than moon, right? See, smaller than moon. Okay, so here you can just give the symbol smaller, or man-made satellite smaller than moon. Okay, then for number 2, the period of man-made satellite with the moon. Okay, so the period is also given already. Okay, so here 27.3 days for the moon is actually longer, right? If compared to the satellite, is only 1.5 hours. Okay, so that means that the man-made satellite will be smaller than moon. Or actually, you can using the Kepler third law. So where they are direct proportional for the period and the orbital radiance. So here the moon have a greater orbital radiance, so the period will be also longer on A1. Okay, so here the period of the man-made satellite will be smaller than moon. Okay. Okay, then the linear speed of man-made satellite, actually you can just look at the given value. Okay, so here we are very clear that the linear speed for the man-made satellite is greater of 7,000. Okay, so here we have another student, Kai Ro Heng. So welcome, Kai Ro Heng. Okay, you may tell me where you come from. Thank you for joining my lesson. Okay, you can just write your answer in the chat room and learn together with me here. Okay. Okay, so just I mentioned already. So the V, or the linear speed for the moon, is greater. Okay. Here is inversely proportional to each other, right? This is a formula just how we derived already. Okay, so here linear speed of the man-made satellite is greater than moon, which is 7,000 compared to 1,000. Okay, then now we go for the another question here. So it's a continue question for the conception question just now. Okay, so based on the answer in B1, B2, and B3, state the relationship between the linear velocity and orbital. And the orbital radiance all come from Cameron. Okay, so it's a very nice place to visit. Okay. Okay, so thank you for joining my class and let me know where I come from. Okay, so here, let us continue. So you can just show me your answer in the chat room also. Okay, so here, linear speed and orbital radiance, you can just go through again, just how we have this figure already, right? So now we discuss about the V and the R. Okay, so here you are very clear that and see they are actually inversely proportional or inversely proportional. So, but here we more prefer to using increase, decrease, and or decrease, increase. Okay, so that means that the linear speed decreases as the orbital radius increases. Okay, so here you can give the answer like this. Orbital radius increases, the linear speed decreases. Okay, this is better than you using inversely proportional. A1. Okay, then the next will be the period and the orbital radiance. Actually, this one just now we also discussed already. Actually, you can using the capital law to explain. But the figure for the period is actually stated in the question now. If let's say you're not clear about the not very clear about the capital law, actually you can using the value given in question. So it's actually directly proportional or increase. So the period increases, the orbital radius increases. So will be the answer. If I say you refer to capital law, or you can straight away refer to the question actually. Okay, so period increases as the orbital radius increases. Okay, so here we have another two students here. Xuanzi, hi Xuanzi. Okay, and Kashia also. Okay, so is it also come from Cameroon? So please let me know where are you come from. Everyone. Okay, so let us continue one. Here the D. What will happen to the main satellite if its linear speed is lower than the orbital linear speed? Okay, this one just now we mentioned already. We have two conditions, right? Okay, so this will be the figure just now we go through together. Okay, so you can see here we have three different routes. So the blue color route is the route where the satellite orbiting at the constant altitude, where the satellite is actually orbiting by using the linear speed, or we can also know as the orbital velocity. Or if I say too fast, the satellite will be moving at the green light, green arrow. Okay, moving to higher position, or moving to the higher position. And then if too slow is what the question asks here. So you can see the red line here will be go to the Earth, right? Or moving to lower orbits. Okay, so here the advice answer will be the satellite will fall into lower orbits, or can write as fall to the Earth. Okay, so both is accepted now, everyone. I think it's not very hard, right, everyone? Okay, then the next will be the calculation. Okay, so the calculation, let's go through the question together. 2 marks. Okay, so the satellite has reached outer space and is orbiting the Earth at an altitude h equal to 2.0 megameter. So mega will be 10 power 6 or 10 power 6. So calculate the linear speed of the satellite when it is orbiting Earth. Okay, so firstly, you should know the formula where relate to G, M, and H here, everyone. Okay, so here the formula will be this: V equal to Gm over R. So this the formula we derived together just now. Okay, so we need to substitute the value. So G will be 6.67 times 10 power 11. The M will be the mass of the Earth, given by question already. Okay, then the R. Okay, so the small r here is actually we need to including the radius of the Earth. So capital R given by the question with 6.37 times 10 power 6. And then you have to change the H 2.0 megameter. Mega have to change to 10 power 6. So please make sure you change everything in SI unit, because the G constant here we use all the parameter or symbol. If you look at G is actually SI unit. Okay, so you press calculator, you can get the answer. Will be the 6,897.431 meter per second. Okay, so you can leave your answer minimum 2 decimal places. Be correct, unit 1. Okay, I think this is a question related to learning standard 1. Okay, so now we go to our learning standard 2. So the learning standard 2, you must able to communicate on the geostationary and non-geostationary satellite. Okay, so here you need to able to differentiate the characteristic of the both type of satellite. Okay, so here the type of satellite, just now actually we had 2 different types, right? But actually, if you look at the overall, the satellite can actually classify based on their position from the surface of Earth or from the center of the Earth. Okay, you can see. satellite orbits around the Earth are classified into 5 types based on their orbital height. Based on their orbital height. Okay, you can see here. So this is actually the extra information for you all. Okay, so here refer to the diagram below. Okay, this diagram actually. So visual representation, the different type of the satellite orbits. Okay, so you can look at the figure. Okay, so we discussed from the LEO, where is a lower Earth orbits, or LEO. So the height, orbital height is about 180 to 2000 km. Is actually the nearest orbits, nearer orbits to the Earth. Okay, so that means that the area will be occupied with more satellite because it's very near to us, so be easy to reach by the scientists now. Okay, then the next here we have the median Earth orbits, we know as MEO. Okay, so here the orbital height is about 2000 to 35,780. Okay, then the third here we have two same orbits. Okay, same satellite orbits with the height of 35,786. So this is geosynchronous orbits. Okay, another one will be the geostationary orbit, is what we need to know in the learning standard 2 here. So you see both of the GSO and the GEO, they have the same orbital height, okay, from the surface of the Earth, which is 35,786 km. Okay, but the difference here, for the GSO or geosynchronous orbits, so the height is at 35,786 km. But you can see orbital plane at an inclined angle to the equatorial plane. So equatorial, that means at the equator. Let's say equator is here. So the orbits for the GSO is actually inclined. It's not exactly at the angle as the equator. Okay, but for the geostationary satellite, geostationary orbits, the position will be equatorial plane as the orbital plane. So that means here you can see, so the green color orbits or GEO is actually 0 inclined angle to the equatorial plane. Okay, so because some of the students, they confused about the GSO and GEO here. So GSO and GEO, actually they have the same orbital height. However, for the GSO, they will have an inclined angle compared to the equator. Okay, but the GEO will be no any inclined angle to the equator. Okay, so another one here we have the HGEO, high Earth orbits, so will be higher than the 35,780 km. So that means that for the geostationary orbits will be only one. So that means that another 4, they will be considered as non-geostationary satellite. What you want? Okay, so here we have NH Han. Okay, so welcome, NH Han. Okay, so let us continue. So now you have to know already, actually we have 5 different type of orbits. Satellite orbits are here. However, for classification in Learning Standard 2, you just need to classify them to geostationary satellite, where it will be at the orbital height of 35,786 km, and there will be 0 inclined angle to the equatorial plane. Another 4 considered as non-geostationary satellite. Okay, so here, so let us go through more characteristic for the geostationary satellite. So here, so geostationary satellite is a special type of the geosynchronous satellite. So that means that here, so because here there is an intersection of the GSO and GEO, right? Okay, so the GSO at some position, actually they're located at GEO, right? Okay, so it orbits at the altitude of 35,786 km above the equator. Equator can be here. Okay, then the next will be in circular orbit. Then with zero inclination, just how I emphasized already, is exactly above the equator. Okay, then the orbital period will be same as the rotation period of Earth, which is 24 hours. Okay, 24 hours. Okay, so all geostationary satellites are geosynchronous satellites because they are located at 35,786 km. Okay, but not all the geosynchronous satellite is geostationary because the geosynchronous satellite, they are actually have inclined angle to the equator plane. Just at a certain position, they are actually zero, and we can classify them as a geostationary satellite now. Okay, so that means that when inclination is zero, so the satellite we consider as a geostationary satellite. And then for greater than zero, which is have an inclined angle to the equator, so they will be considered as non-geostationary satellite, even though they have the same orbital period with the GEO here. Okay, so that means that here we can classify between the geostationary and non-geostationary satellite we table here. Okay, so the first, so the geostationary satellite will be located at the geostationary Earth orbit, which is 35,000 plus km, right? On the equator with zero angle of inclination to equator. Only one, Okay, then for the others will be considered, they can located above or lower than the geostationary Earth orbit. So they'll be not located at the exactly geostationary Earth orbit. Then second difference here will be the orbital period is 24 hours, same as the Earth rotation period. Then for non-geostationary satellite, we consider it will be longer or shorter. Okay. Okay, then the rotation direction for the satellite, for geostationary satellite, they will be same direction with rotation of Earth, which will be from west to east. Then for non-geostationary satellite, they are actually can be same west to east or another way. Then number 4, here they will be, it always appears stationary to an observer on the Earth's surface. So that means that if we observe the the geostationary satellite, it will be always at the same position. But for the non-geostationary satellite, so to an observer on Earth, the satellite appear constantly change its position. So that means the position will always change. This will be the characteristic for non-geostationary satellite. Okay, then the next here we have another 3, some more for comparison. So for geostationary satellite, so its orbit is always directly above the Earth equator, just like I explained to you already. It will be zero inclination. Okay, then for the non-geostationary satellite, it will be not have to be directly above equator, Earth equator. Then the next here, okay, so for the geostationary satellite, it is actually used to communication purpose. Then non-geostationary satellite, they will be for others. They can be weather forecasting, navigation, imaging Earth surface. Okay, so example, communication satellite, here we have MEASAT or Astro satellite. Then for non-geostationary satellite, it can be more than that. You see, GPS is actually located at MEO, just how we explained already, or medium Earth orbits. Then ISS, International Satellite, okay, is located at LEO, is very near to Earth actually. Okay, so it's at low Earth orbits. And then Tionsat 1 is located, is also at LEO, but is orbiting the Earth at the pool orbits. Okay, so this will be the difference characteristic between the geostationary and non-geostationary satellite. And here it can be classified to most simple, where actually this is from textbook. Okay, so let us go through the English version. So here is the BM version now. Okay, so for English version, you can see here. So geostationary satellite and non-geostationary satellite, they have three similarity. The first, it will be orbits the Earth for both. Then they have the same linear speed. So V equal to square root GM over R. Then the third will be the period, orbital period can be calculated by using the capital law. This formula actually is not new. T equal to square root 4 pi square R cubed over GM. Actually, this is a Kepler third law. So where we have a relationship between the period together with the orbital, where will be T square directly proportional to R cubed. So these three will be the similarity between geostationary and non-geostationary satellite. Okay, so what is the difference? Okay, so we look at the first here. Okay, so here you can see the direction motion same as the direction of Earth rotation. So will be rotate from west to east, not just what I mentioned to you. Then for the non-geostationary can be same or not same. Okay, then the period for the geostationary satellite will be same as the rotation period for Earth, which is 24 hours. Then for non-geostationary, they will be shorter or longer. Okay, then the third differences here will be the geostationary satellite is always above the same geographical location. That means the observer will be always observe on the surface of Earth for the satellite, like not moving. Then for the non-geostationary satellite, above different geographical location, they will be always change position. Okay, then the geostationary satellite is mainly used for communication. Then for non-geostationary satellite will be used for Earth imaging, GPS, weather forecast. Then the example of the geostationary satellite, there will be MESAT. This is a example of the communication satellite. Then for non-geostationary satellite, we have Tionsat, Rajasat, PIPITS, and ISS. ISS is international satellite, okay? Space satellite. Okay, so here will be the summary for the Learning Center 2. Okay, so now we go for the third learning standard, what you want. Okay, if you have any question, you can just tell me in the chat room what you want. Okay, so the third learning standard, you must be able to conceptualize escape velocity. Okay, so here you need to understand or how the object able to escape from the Earth actually here. Okay, so the formula we are going to use will be this. V equal to 2gm over r. Just now, for the linear speed, our formula will be gm over r, right? Okay, so later I will show you how we get this formula. Okay, so now first is the definition for the escape velocity. Okay, so the definition normally will be come out for the first question for most of the individual question, right? Okay, so here escape velocity, here I'm using a simple VE, but if I say for the formula sheet at the real exam, they just put V okay, for linear speed and also the escape velocity. Okay, so the definition here will be the minimum velocity needed for an object on the surface of the Earth to overcome the gravitational force and escape to the outer space. Okay, this will be the definition. Okay, so now let us derive the equation for escape velocity. Okay, so here we're using the principle of conservation of energy. So you can see here EI and EF. Okay, so EI is total inertial energy. EF will be total final energy. So that means the energy can be changed, but the total energy before and after for a reaction is actually the same. Okay, so for initial energy and final energy, so they actually involve for two types of energy, which will be the gravitational potential energy. You can see here, PE, gravitational potential energy. Another one, KE, will be the kinetic energy. I referring to initial, F referring to final. Okay, so it will be like this. So kinetic energy initial plus potential energy, gravitational potential energy initial equal to final. Okay, so here the kinetic energy actually you know already, right? Since you learn at Form 3, the equation will be 1/2 mv squared. Okay, so the V referring to the velocity. Okay, so you can look at this figure. U will be the initial velocity where the object is on the surface of the Earth. Okay, then V will be the velocity of the object when moving to infinity, or moving at infinity. Okay, so we have this formula, you see, 1/2 mu squared. So I'm using U represent initial velocity of the object. Small m will be the mass of the object. See here, it's already set in the figure already. Okay, so here you see why we have a negative GMN over R. Okay, so for your syllabus, you actually no need to understand how this formula is derived. So you just need to memorize the gravitational potential energy, PE. It will be with the formula of negative GMN over R. Okay, so why we have negative? Okay, so here tell already. So why GMN over R we have negative? So because the gravitational potential energy in space is defined relative to 0 at infinity. Okay, so we assume that when an object moving further and further from the Earth, so at the infinity, that means it's very far already. So the object will be attracted by gravitational pull. So you can see here, we have the gray region where we know as the gravitational field of planet. Okay, it will be this, you see. Okay, so you can see initially the object from the surface of the Earth need to escape, moving further, okay, until out of the gravitational field of planet. So when the object is moving out of the gravitational field planet, so that means that the gravitational potential energy will be 0 already. Okay, so because it's not able to attracted by the G already. Okay, so we assume the PE at infinity or gravitational potential at infinity is actually 0 lah. Okay, so that means the object within the gravitational field of planet will be actually attracted by the gravitational pull. It's not move freely, so they will be given by negative. Okay, so the negative sign tells us that the object is within gravitational field, just like I mentioned already, and bound to the central mass. So that means it's attracted to the central mass. So in this figure will be Earth lah. So the closer the object is to the mass, that means that when the R is smaller, R will be here. Depends at the position where of the object. Okay, so the smaller r, that means they will be closer to the Earth already. So the more negative is potential energy. So that means that the object is tightly bound by the Earth. So we can conclude that as r increases, that means that the object moving further from the Earth, the potential or gravitational potential energy become less negative. So the gravitational potential energy increases. Okay, but will be zero when reach infinity, where it is completely free from the gravitational attraction. Okay, so this is why we have negative GMN over R here. Okay, so when at infinity, so this V will be equal to 0. Equal to 0 because it's not, it's a maximum of the gravitational potential energy already. Okay, then we can cancel out this. Okay, then for the RF, so when at the infinity, so that means that the figure below the fraction is very big, so it's actually close to the 0. So again, we can cancel out. So we left the equation become 1/2 mu square minus GMN over R. Okay, so we rearrange, will be this formula. So the formula here actually tells us that the object need to have minimum kinetic energy to overcome the gravitational potential energy, so that it can escape from the Earth. Okay, then if at surface of the Earth, so that means the Ri here is radiance of the Earth. Okay, and then the U here is escape velocity, or is the velocity where the object start to escape. Okay, so we can get 1/2. Okay, we substitute U to become VE. Then we substitute Ri to become R. So we get this formula. Then we rearrange, we get this. Escape velocity equal to square root 2 GM over R. You want? Okay. So factor affecting the escape velocity of the object from Earth's surface. So that means here we can discuss by using this formula. Okay, actually here we are using VE already now. So it's affected by G is a constant value, M is actually constant also, right? However, if we look at the M and R, they will be the only two parameters will be affecting the escape velocity. Okay, it will be mass of the Earth. Second, there will be the distance of the object from the center of the Earth. Okay, okay, so the escape velocity does not depend on mass of the object M here. So you can see there is no any small letter m. Okay, so that means here they will be only impacted by GM and R only. Okay, then the number 5. Okay, so now we can find out the escape velocity of the Earth by using the formula we derived here. So the mass of the Earth will be 5.97 times 10 power 24 kg. Okay, then R will be 6.37 times 10 power 6 meter. So we just substitute into the formula. It will be this value and this value. So we get the escape velocity will be 11,181 meter per second. Or we can change to km per second will be 11.2. Okay, so this is escape velocity for the object on Earth. Okay, so before we continue our last learning center 4, so if one we can take 5. Okay, so please stay tuned. Okay, we will be back about 1 minute later. So see you. Okay, welcome back everyone. So here we go for our last learning standard. Okay, so solve problem involving in the escape velocity. Okay, so here actually the learning standard here will be together with few SPM format question for paper 2. everyone. Okay, so here look at the question number 2. Okay, so the escape velocity at the height of 0.2 r from a planet of radius r is 10 km per second. So what is the escape velocity from the surface of the Earth, of the planet here? Okay, so first we have the info where the escape velocity from the height of 0.2 r is actually given as 10. So we want to know how about the escape velocity when the object is at the surface of planet. That means it's at the r. You want, Okay, so we're using this formula. So first, escape velocity at the position of 0.2 r. So that means here, this is the planet with radius of r. Now the object is at here. Okay, so the planet is here, sorry. You see escape velocity at this. So it will be at 0.2 r. So that means the total altitude here will be 1.2 r. 0.1. Yes, we just take 5 for A1. Okay, so we have actually 3 questions for this learning standard. A1. So this all will be the SPM format question now. So it's actually related to the last learning standard on Jimmy. Okay, so here the V1 assume have the at the location of 1.2 r here. Then the second, okay, so we substitute in this formula. Okay, so the VE here will be 1. Then the R here will be 1.2. Okay, then we can rearrange to become this. How we substitute all the value here. Okay, so hi, we have Hui-Xuan. Hi, Hui-Xuan. Welcome to our lesson. We are at last learning standard already. So we have 3 questions going to discuss at this learning standard. Okay, so here, assume escape velocity at the surface will be V2. So we have this formula. So we using 2 divide 1. Then you see 2 divide 1. V2 with this divide 10 and this. So we rearrange, we get this. Okay, so we can cancel out R, cancel out 2GM. So that means here it will be V squared over 10 equal to 1.2 square root. Then we rearrange again, so we get answer is 11.1. Okay, 11. So answer is very clear with B down here. Okay, so this is one of the problem solving involving the escape velocity. Okay, so the question number 3 here is a paper 2 question. It's a paper 2 question. Okay, so diagram 2 shows a spacecraft launch into the space from the surface of the Earth with the escape velocity. Okay, so what is the meaning of escape velocity? Okay, so the escape velocity definition just how we explained already. So with this, the minimum velocity needed for an object on the surface of the Earth to overcome gravitational force and escape to the outer space. So this is the definition where you can get from the slide just now we discussed. Okay, if you miss out, you can just pull to the front. Okay, so you can see the definition already, or you can get to from textbook also. Okay, then so here the question. Okay, I straight away get the answer. Give you the answer already. Actually, the question will be this. So calculate the escape velocity required by the spacecraft to escape from outer space. Okay, so you can see here is actually the planet is Earth now. So the M will be this. Then the radius given is this. So from the formula, VE equal to square root 2GM over R. You just substitute everything. Then you can get the value. This is the value just how we discussed also. Okay. So it'll be 11,181.3789 meter per second. Again, you can give minimum 2 decimal places for answer. Okay, then for C, if the escape velocity of the spacecraft is 8,000, so will it be able to escape? Explain. Okay, is it able to escape? 8,000. Just now we calculate from B. The escape velocity is 11,181. So 8,000 is actually below this value, right? So the answer here should be no, or 2 marks, or no will be first mark, and then give the reason. So the reason here will be the velocity of the spacecraft is actually less than the escape velocity. So answer no will be first mark. Second will be the velocity of the spacecraft is lower than a escape velocity. Okay, so now we go for question number 4. Okay, question number 4. I should we give you the answer really easy. Okay, so here, Titan is the moon that orbits the planet Saturn. Okay, so this is the one of the moon and the planet of Saturn. So the mass given at this 1.35 times 10 power 23, and then the R will be given as this value, 2,575 km. Okay, then the question gives you the rocket mass 1 times 10 power 5 kg. Okay, then is launched vertically from the surface of Titan with the velocity equal to escape velocity. Okay, so now the question asks you about the escape velocity for Titan. Okay, again, we have to use a formula, right? The formula will be square root 2 gm over r. So here, why 3 marks? Okay, so first 2, no problem, g, no problem. Then the m given at this is the m. And then here the r is actually km, right? You have to change to meter. So this will be the first mark. Second mark, substitution over rho. Then you get answer 2,644.58 meter per second. Okay, so the question B asks you, set the change in escape velocity in 2B if the mass of the rocket is twice. Okay, so answer here is actually no change. Why? So we have to using the formula, you see. So the escape velocity depends on G is fixed. Then M will be the mass of the planet, right? R will be the radiance of the planet. So here the small m, the mass of the rocket is no any impact for escape velocity A1. So that's why there will be no change. Okay. Okay, so the question 5 will be last. So here, this is a section B question or modification and decision making question. Let us go together. So here, diagram 5.1 shows 2 satellites K and L and equal mass orbiting the Earth at height of, okay, so here we 2 height. So the satellites are orbiting at the certain linear speed in the same direction with Earth, but have different orbital period compared to Earth. Okay, so that means that the orbital period for the satellite here is not 24 hours, right? So name the type of satellite K and L. So is geostationary or non-geostationary. So here already tell us because of not 24 hours. So this is actually non-geostationary satellite I1. Okay. Okay, then B, explain the changes of the motion if the satellite speed is equal to linear speed. Okay, this one actually just now we discussed few related question already. Okay, so you can see if the linear speed no change, so that means the R will be also no change. So they will be orbiting at the same altitude. Okay, you see the radiance of the satellite orbiting the Earth, it depends on the speed. This is what I show you here. Okay, so when satellite move at a linear speed, that means don't change. The satellite will orbiting at a constant altitude. They will be stay at the same orbit lah. Okay, then the next here, speed of the satellite does not equal to linear speed. So just now I mentioned to you, we have two conditions, right? So there will be, look at the rate route, where it will be slow, right? When it's slow, they'll be moving at the lower orbit or towards or fall to the Earth. Then if greater than orbital velocity or greater than linear speed, they'll be moving to higher orbits already. So that means we have to give two conditions. First, when the satellite moving less than the linear speed, they'll be at this position. So the satellite will fall to the lower orbits than initial orbits. Initial orbit can be the blue color orbits now. Then second condition, when the satellite move more than linear speed, the satellite will be rise to a higher than the initial orbit. You'll be look at the green color line already, arrow already. Okay, so here will be 2 marks. Okay, then here we have one calculation question related to gravitational potential energy. What you want? Okay, so you see satellite L has mass 1000 kg. Just now the question give L and K have the same mass, right? But here, if the question changes to, if the mass of the K is double for L, so now we compare their gravitational potential energy. Explain. Okay, so formula will be Gmn over R. So if you get more negative value, that means the potential energy, gravitational potential energy will be actually smaller and more close. But here, more close comparison if both have the same mass. But if they have a different mass, they will be different already. However, the negative and the PE is still valid. Okay, but closer here it depends on the mass also. Okay, so here, the formula Gmn over R. Okay, so here we look at the satellite K. Okay, sorry, we look at the satellite K. Okay, so the satellite K, the distance will be, the R will be 543,000 km, right? So we have to change to meter lah. So we get negative 1.1468 times 10 power 9. Okay, then for the L, okay, so here the mass is 1000. Then the R here will be also changed already. Make sure you change to km meter. Okay, so we get negative 1.10 times 10 power 9. So that means the PKE is actually more negative. If more negative, that means that the satellite K is actually have less potential energy, although it's actually further, right? Because here the mass will be give the impact for the value of PE here already. So the discussion, the gravitational potential energy K, you see K is more negative, right? Compared to L. So K has less gravitational potential energy. That means that it is more gravitationally bound to the Earth. They will be more attracted by the pull of gravity. Okay, so although the K is further from the Earth, is greater mass result in a stronger gravitational binding. Okay, so this is a case where the mass can actually give the impact for the gravitational potential energy. Okay, so the closer to the Earth is compared for the same mass only, you want. Okay, so now we go for the D last already. Or is a decision making question. Okay, so everyone, you can just tell me which satellite which we actually need to select, P, Q, R, or S. I discuss one by one together with you. So you tell me what is the satellite actually we need to choose. Okay, so here, the question will be like this. Diagram 9.2 shows a satellite. Okay, this is together with the solar panel and the antenna. Okay, so that means here is not only apply the knowledge for subtopic and 3.3, but also others. Okay, you see, Table 9 show the characteristic of 4 communication satellite. So this is a keyword. Just like I tell you already. When this is a communication satellite, what type of the satellite you need to choose? Okay, so this is related to the subtopic 3.2 today. Okay, so you are required to determine the communication satellite that's always above the same geographical location on the Earth's surface. You see, here actually tell you the clue already. So the character here will be always at the same location, right? Q. Okay, so Jimmy give Q. Okay, so let's go through whether it's Q. Okay, so others, you can also share your answer in the chat room besides of Jimmy. So thank you, Jimmy, for your response. We see together whether you correct or not. So expand the suitability of each characteristic of the satellite. So hence, determine the most suitable satellite as communication satellite. Give reason for your choice. Okay, so here, the first, just now we mentioned, this is a communication satellite. So we have to choose geostationary. We cancel the last two. So we don't need to see these two anymore. So can be Q. So Jimmy can be correct. Okay, then the period, just now I mentioned to you, if this is a geostationary satellite, it's supposed to be 24 hours. So that means the P is already. So Jimmy is correct. Ivan. So the solar panel here, we are very sure that must be more, but you have to give the reason. Diameter of antenna is also need to pick Y. Okay, so here we go through together. So again, we can give the answer in the table. Okay, so the first, we discuss about the type of satellite. Here will be geostationary satellite, as mentioned just now. Will be this, right? Okay, reason. Here, because of the, you can give any suitable reason besides of the orbital period here. Actually, you can give because the direction of the geostationary satellite is same as a direction rotation of the Earth. Actually, it's also accepted. Okay, so the second orbital period we are very clear will be 24 hours. Reason, same as rotation of period of, as I mentioned to you just now, right? We can give the suitable characteristic where is the geostationary satellite. Okay, then the solar panel here must be more. Why? Because when we have more solar panel, we can receive more sunlight so that we can get more energy, electric energy, and can give more power, right, for the satellite to work. So here, more electrical energy or power. Then the next here will be the diameter antenna. So the antenna purpose is used to send out the signal or receive the signal. When we have the bigger diameter, that means that it will be easier to get more signal, right? Okay, so here we have the big. More signal will be received or transmitted. So answer is correct from Jimmy, which is Q. So you can just copy the first, third, fifth, and seventh at here. Then you can get the full marks already. So that's all for actually for discussion today. Okay, so this is the last already. Okay. So thank you everyone for joining my lesson today. So now I want to share to you the link schedule for today's lesson. Okay, you may fill up the form with any email you are available. So please complete that form within 30 minutes. Okay, so thank you, Jimmy. Jimmy, is it you are Form 5 students now? Because I see you also last year. Okay, so you can just reply me in the chat room. Okay, so thank you everyone for together with me until here. Okay, so please share, like my lesson today to your friends so that there will be more students can benefit from my lesson today. Okay, so don't forget to follow the next physics classes where we have 2 classes here for Form 5. There will be Non-DLP here on every Friday, 9:30 p.m. Then for Form 4, there will be 8:15 p.m. every Sunday. Okay, so you are from Form 5. Okay, so I think that's all for today's lesson. Thank you all of you for together with me here. Okay, so bye bye everyone.